Hello, welcome to Module 11. In Module 11, we're going to continue the concept of graph coverage, but we're going to see the way of testing in another different angle. And this is when we use the data flow to do the test coverage criteria. So let's get started. We still stick with this graph-based technique that we have discussed so far, and we rely on the structure of the graph. But now we're going to look in a deeper detail on how the data flow inside the graph and how can we derive the test cases from those data flows. All right. So today we're going to discuss a few things. First, we're going to analyze how the data flows within the software artifacts. Second, we're going to understand how we can integrate these data flows into the graph model and how to do software testing. And the third one is we're going to use these data flow that we have, and we will apply the three coverage criteria consisting of one, all depth coverage or ADC. Second, all uses coverage or AUC. And the third one is all DU parts coverage or ADUPC. Okay. So let's get started with the graph coverage criteria. So when you have a graph, we have these coverage criteria that we set a test requirement, right? We discussed in the previous module that the test requirements are the requirements that our test must satisfy in order to fulfill the coverage criteria of that testing. So given a set of test requirements TR, and we have this criterion C that applies to the test requirement, we have a test set of T, and the test set T will satisfy C on the graph if and only if every test requirement in TR, there is a test part that meets such test requirement. Okay, simply put, this means we select a criterion first. Let's say node coverage, edge pair coverage, for example. And then we define what should be the test requirements for those criteria. And then we create a set of tests, and then we check whether this set of tests satisfy each test requirement. If every test requirement is satisfied, then we fulfill such criterion. Okay. In the last module, we discussed this coverage criteria called structural coverage criteria, where we look at the graph in terms of the nodes and the edges. So we look at the structure of this graph, and we try to cover the most of the structure as much as possible, whether it's going to be nodes, whether it's going to be edges, or it's going to be parts. But today, we're going to focus on this one. So we're going to study data flow coverage criteria, where we annotate the graph based on the variables that are inside the program that we derive the graph from. So the key goal of the data flow criteria is we want to ensure that the values are created and used correctly. Okay, so we don't just care about the structure, whether the test visit the nodes and the edges or not, but we now care about the values. The values in the program can be the parameters, the variables that are created, when it is created and when it is used. So we put the focus on these criteria more. And how do we do that? We're going to focus on two things. So the first thing is called definitions, and the second thing is called the uses. So let's see each one of them. First, for the definition, or we call it def for short. The definition is a location where a value for a variable is stored in the memory. This means initialization of a variable. Okay, so whenever you initialize a variable or you assign a value to a variable, that is also the def actions, because that is when the value of the variable has been stored in a memory. The second thing is called use right? So use is the opposite. It's a location where a variable value is accessed, okay? So this is when you call the variables values. I think better to say read the variable value, sorry. Okay. So the value that are carried from def to use, we will call them the DU pair. Okay, so this stands for def and U stand for use. So we have def and use pairs. We can call them definition use, def use, or for short, we just call them DU. Okay. So with this data flow coverage, we're gonna have a few steps. The first few steps is very similar to the structural graph coverage criteria. So you first develop a model of the software as a graph. So you turn the software code into a CFG, like we have done in the previous module. And then we're gonna integrate the data flow into the graph. And then we start defining the test requirements. And then we find the parts that toward those test requirements, okay? So some of the definitions that we need to understand. So the first thing is def. When I write def of something, that means it is a set of variables that are defined at that particular node or at that particular age. So the def of n will show a set of variables that are defined at the node n. And the def of E is the set of variables that are defined at the age E. What's the def? Something like this. Int x, int y equal x, okay? Int z equals z plus x. Or when you assign some value like this, p equals 1, that also the same. Okay, so this is def. But at this location, you also use the value of x and z as well. Okay, so def is when we initialize a variable or we read or we assign the value to the variables, and use is when you read the value from those variables. Okay, so if I say use of n, the same thing. We use the variable at this node n, and the use of E is a set of variables that are used at the age E. Okay. And the DU pair is a pair of locations. So L stands for locations. We have LI and LJ. So LI is the place that it is defined. And LJ is when it is used. So let me show you a very simple example. If we have this pretty simple program, oh, let me remove this first. Int x equals 0 while x less than 10 x plus plus. Okay. So we would have this as node 1. This will be node 2. And this will be node 3. Okay, so you have node 1, node 2, node 3, and then you have the final node here. So node 1 represents this initialization of x. Node 2 is when you have the loop, right? So while x less than 10, if x is still less than 10, you go here, and this is x plus plus, okay? But if x is more than 10 or equal to 10, you jump to the final node. And if it's not, then you go back to the loop header. So this is a pretty simple program and a simple graph. And what is the def, right? So if let's say we have a def at node 1, we would have x, because x is the variable that got defined at node 1. And what are the depth at node 3? So the depth at node 3 is also x, because x has been increased the value at node 3. We also have the use. Okay, so the use at node 2 consists of x, because x is read at that node to compare with the value of 10. Okay, and we also have the use for these two edges. Okay, so the use at the edge 2, 3 is x, and the use at the edge 2, 4 is also x. Okay, so this represent the value that is defined and the value that is used. And when I say du pair, du pair of the location 1 and use at the location 2, we get the x as well, because it is def at node 1 and it is used at node 2. Okay, I can also say du of 1 and 3. Okay, because x is def at 1 and it also used at the node 3. I forgot to say that at this particular node, there is also a use of x as well, because x is read, because x plus plus is actually x equals x plus 1, right? So both def and use occur at the same node. Okay, so this is a pretty example just to get you familiar with the concept of def and use. Okay, so let's see an example of what are the depth uses and the du pair from this graph. So we have this graph, which is a single entry, single exit graph. And you have the value of x initialized here, x equal 42. And then along the blocks, you have used the value of x in the node 5 and the node 6 here. So at node 5, you will see that z equals x multiplied by 2. And at the node 6, we'll see that z equals x minus 8. So if we list all the depth, we will see that there's a depth of x at node 1. And at node 5, you have the depth of z. Also at node 6, you also have the depth of z. For the uses, we have two locations, this location and this location. So the use of node 5 consists of x, and the use of node 6 also consists of x. When we write the du pairs, we would get 1, 5, which is this one, from this to this. So x is def here, it is used here. Another one is 1, 6, which is coming this way. You can have many ways to come to 1, 6. Okay, so you have def here and use here. You can also go to the top as well, like go this and this. Also for 1, 5, you can also go this way, 1, 2, 4, 5, or 1, 1, 3, 4, 5 as well. Okay, so all the variables that involve in a decision, such as in the if statement, in the while loop statement, or the other loop statement, we assume that they are also used on the associated edges. Okay, so let's say we have this graph starting at node 1. You have seen this graph before in the previous module, and there is a decision here. So if a less than b, we go this way. If a equals b, we go this way. And if a is more than b, we go this way. So let's say we have the def at node 1. So we def a and b at node 1. In this 8, 1, 2, we're going to have the use of both a and b, because we read both the value of a and b and compare them. Also, in this age 1, 3, you also have the use of a and b in the same explanation. Okay, and the H14 also has the use of A and B as well. So please be careful that when we have the decisions, you would have the use on the edges of those decisions. So next is another definition that we need in order to define the coverage criteria. The first one is called depth clear. So depth clear means it is a path from one location to another, and it will be called depth clear if that variable is not given another value on any of the nodes or the edges. That means the variable v is not overwritten on the path. Okay, so if any path is called a depth clear path, that means the path of that variable starting from the depth to any location specifying in the path, that variable has not been assigned another new value. So that's why it's called clear, because the value still stay the same. Okay, the value stays the same. Okay, so the value given in the depth should go to some possible uses. It might go to one use, it might go to a few uses, or it might go to all the uses. But if we have a depth variable, some of them also possible that it might not reach any particular use. Why is that? Because it might be the possibility that the path in the graph is not reachable. So there is no path go from the location that the variable is defined to the location that the variable is used. It is also possible that the value might be changed by another depth along the way of the path before it reaches the use. So in this case, these two paths are not depth clear. Okay, either it cannot reach the use, or it cannot use the same value because it is overwritten over the course of the path. Okay. The next one is called reach. So if we have a depth clear path from one location to another with respect to variable v, the depth of v at the location that it starts will reach its use at the location that it ends, lj. Okay. The next one is called a du path. A du path is a type of simple paths. Okay, so first it is a simple subpath that is depth clear. So the first thing is that it shouldn't be any assignment along the way. So if it's respect to the variable v, then the whole part of this variable starting from depth to use should not be any assignment or any depth in between. And we would call that a du path. And when we write the du path, we would use du, and we can add the starting node, and we can add the ending node, and we add the variable that we want to specify that du path. But if we leave the ending node here, so if we have only the starting and the variable, then it will be all the possible du path that start from the location ni. So we keep these, we only use a simple path because we don't want to have the loops, right? Remember the concept of simple path and prime paths. We want to avoid the number of loops. So we don't count the paths that have internal loop because we want to have the small number of paths. So if we have this example, the same graph again with the same depth and the same uses, we have the depth at 1, 5, and 6 for variable x, z, and z. And we have the uses at 5 and 6 for variable x and x. Okay, we have these du pair for variable x. You have 1, 5, and you have 1, 6. So if we want to find the du paths, the first one is the du path from 1 to 5 of the variable x we would have two parts, which is 1, 2, 4, 5. Another part is 1, 3, 4, 5. And if we want to find another du part of 1/6 of the variable x, so you can go from the top 1, 2, 4, 6, or you can go from the bottom 1, 3, 4, 6. All right. So we have this kind of understanding of the du parts now. So we have just a few more definitions for you. So the first one is called a du part sets. So if we have all possible parts starting from node ni of the variable v, we call this a def part set. Okay, it's starting from def only, right? So we only have the def location. So the def part set will be all the simple parts of the variable v that are defined in a given node ni. And another one is called a def pair set. A def pair set is when we have def and use and the variable. So if we have this, it will be all the simple parts of the variable v from a given definition at the node ni to a given use at the node nj. All right. Just to sum up, def part sets has only the starting point. The def pair set has both starting and ending point. Okay, so if we have the same graph again, what would be the du part set? So if I say the du part set of 1 and x, okay, sorry, this should be def part sets, okay. So the def part set of starting at node 1 of the variable x, you would get this, and these parts. But if we categorize by the du pair, then you would have two sets, the one that go from 1, 5 and the one that go from 1, 6. We can double check quickly here that it starts from 1 and end at 5. And another one, it starts from 1 and end at 6. Okay, both of them. So how the Turing works with this kind of du parts. So with this kind of du part, we say that a test part T that we have will du tour, okay, any subpart B with respect to the variable V. If that test part P tours the subpart D and the subpart is also def clear. All right, there are many definitions being used here. So let's see it again. So if you have a test part P, it's gonna tour a subpart D of any variable V when that subpart contains is a part of the test part and it is also a def clear part. All right, so let's see if we have the same graph again. Okay, we have this def part set and we have these du pair sets, which is the same as the slide that I showed before. And if we have the test part 1, 2, 4, 5, 7, okay, 1, 2, 4, 5, 7, it's gonna du tour this du part 1, 2, 4, 5 because 1, 2, 4, 5 is here, and also among these part 1, 2, 4, and 5, there is no def of x, so it is a def clear part. Okay, it satisfies both requirements. So now we can say that the test part P here du towards the du part 1, 2, 4, 5. All right. Okay, so these are the basics that we have, and we understand the data flow now. We understand the concept of def and use. Now we're going to move to the data flow coverage criteria. We have 3 coverage criteria here. The first one is all def coverage, where we ensure that we go to the use of every def. The second one is called all uses coverage, or AUC, where we ensure that we get to every single use. And the last one is all DU parts coverage, or ADUPC, where we follow all the possible DU paths in the program. So let's start with the first one. So the first one is all depth coverage. So all depth coverage is for each set of the DU path S that we have. Sorry, I keep making a typo here. For each set of the depth path S, the du of any nodes and any variable v, the test requirement will contain at least one path in D in S, okay? One path D in S. And for it, that means for each depth, at least we need one use to be reached. Okay, let's see an example to understand this better. We have this graph, same as the previous one. We have the following DU path sets, okay, starting from node 1 of the variable x. One thing to be keep in mind is that when we do this kind of all depth, all use, and all DU path coverage, we calculate it based on each variable. Okay, so this is the x variable. We define all the DU path sets, and then we have these depth path, the depth path set, and we have this depth path set of 1, 2, 4, 5, 1, 3, 4, 5, 1, 2, 4, 6, and 1, 3, 4, 6. So the test requirement for X says that the test requirement will contain at least one path D. Okay, so we just try to go to one possible use of this depth. We have only one depth, which is at 1. But we have two locations of the use, which is at 5 and at 6. But we choose only one use. So I pick only this one that I def at 1 and I use at 5. And I can find the test part of 1, 2, 4, 5, 7 that satisfy this all def coverage. The second one is the all uses coverage. The all uses coverage is pretty similar. We will have the DU path set S. The test requirement will contain at least one path D in S that for each of the depth, all the uses must be reached. So what's the difference here is that instead of just one single use, we want to get all the uses. So for this, we have the following DU pair sets, 1, 5x and 1, 6x. So starting from 1 at both of them, but they end at a different node. So this one used at 5 and another one is used at 6. So the test requirement now need to contain both of them. So the test requirement contain 1, 5, 1, 2, 4, 5, which is the DU of 1 and 5, and 1, 2, 4, 6, which is the DU of 1 and 6 of the variable x. So when we have these kind of test requirements, you can also derive the test part that satisfy the test requirements. And we have these two test parts. So this one satisfy this one, and this one satisfy this one. The last one, as you might already expected, is called all DU paths coverage. So if we have the following DU path sets called S, then the TR will contain every part in that set S. And this means for each of the depth use pair, all the parts between depth and uses must be covered. So we list the DU path sets again for this graph. Okay, we have the same DU path set as the previous one. So this means that the test requirement will need to contain all 4 of these DU paths. And then you find the test part that satisfy these 4 test requirements. So this one is this one, this one is this one, this one is this one, and this one is this one. Okay, easy peasy, right? So the last thing, I want to show you the real case where we have software code and then we need to transform it into a graph. So if we have this program, this is actually a method. It's a method called path. Path accepts 1 and 2 parameters. So this is method parameters. And it also initializes a few variable. Okay, so this is local variable. And then the rest, the local variable are used, okay, and also depth at at each specific locations. Okay, so we use this kind of understanding of the graph, and we convert this program into a CFD graph. You're gonna get the graph that looks something like this. Okay, but what different here is that we need to look into the details of what are the code statements or the basic blocks that belong to each of the nodes. So the node 1, you have subject and pattern coming in. At node 2, you have these basic block of all the initializations of the variables. And then you start having this, which is the if statement here. Sorry, the while loop header here. So you have this decision that contains 2 sides. So you can go here or you can go here. And then you come down, you have another decision, and you come down, you have another decision, so on and so on. Okay, so I write down the code that belongs to that each basic block and each node here. So you might need to take some time, a few minutes, to go back and forth between the code and the graph to understand how this graph become constructed and what are the value of the statement that belongs to each node in the graph. So let's pause the video a bit and going back to see the code and compare to the graph that you have. Okay, so after you have understand how the code has turned into this graph, let's move on and apply the concept of graph coverage criteria based on the data flow to this graph. So with the graph that we have, next we're gonna annotate each of the nodes with the depth and the uses at each of the nodes. So at node 1, I have the depth of subject and pattern. At node 2, I have the depth of these following local variables, and I have the use of subject, pattern, and not found. On the edge 311, I have the use of isub, pattern length, subject length, and its path. Also the same for the edge 34. At the edge 410, also the same for the edge 45, which are the decisions. I have the uses of the subject, isub, and the pattern. At node 5, I have the depth of RTN index, ispath, and ipath, and I have the use of isub. At the edge 610 and the edge 67, I have the uses of ipath and pattern length. At the edge 7.8 and 7.9, I have the uses of the subject, pattern, isub, and ipath. At the node 9, I have the depth of ipath and I have the use of ipath. At the node 8, I have the depth of RTN index and ispath and the use of not found. And lastly, at node 10, I have the depth and use of the isub. Okay. If we go back a bit, we would see that the depth and use at the same node is caused by these plus statement, right? So when you have these plus statement, actually you have this code, right? So iPad plus is actually iPad equal iPad plus 1. So this is depth and also use at the same time. So that's why we have this kind of depth and use at the same node here. Okay, so if we try to apply the concept that we learned, so let's say we're gonna start by using the analysis on the variable isub, and we're gonna use this depth path set starting at node 10. So if we start at node 10 with the variable isub, we're gonna have the following DU path sets. And if we classify them into the DU pair sets, you're gonna have the following paths belong to each pair of the depth and used. Okay, so let's go back a bit to look at the graph. We want to know that at this depth of isub, where can it go? So 10 can go to 3. It can go to 4. It can go to 11. It can go to 5. It can also come back to 10. It can go to 6. It can go to 10 again. Can go to 7. Go to 8. Go to 9 and come back to 6 and to 10. Okay, so from node 10, you can go pretty much almost anywhere. But remember that these must be the simple parts. Okay, so you stop when you reach itself, so that you already got a cycle, and we won't go any further. Okay, or you stop when it reaches the use of the variable. I mean, it would be the use and also the um, the stop. But this one, it is the use and also the end of the cycle as well. But you won't go any further to have anything as internal loop inside the parts. All right. Okay. So let's try to analyze it a bit. So if we have node 1, you have the def for the variable subject. And the use for this variable subject will be at node 2, and it also be used at node 410 here. So you use the subject here. At node 4.5, you also use the subject here. At node 7.8, you use subject here. And also the age 7.9, not node, sorry. Age 7.9, you also use the subject. So if you want to do all depth coverage for this subject, starting at node 1, we would have just one test requirement, which is 1 to 2, because I just want only one use for all depth coverage. And I can find the test part of 1, 2, 3, and 11. And that would be all for all depth coverage. Okay. If we move to another variable, let's say if you are interested in the variable, just a moment. If you are interested in the variable pattern, the pattern also defined at node 1. It is used at node 2. It is also used at the decisions here at the edges 410 and 4.5. And it also used at the decisions at the edges 7.8 and 7.9. So the same thing here. If you want to find the ADC for the variable pattern, you have the test requirement of 1, 2, and then you can find the same test parts to satisfy that test requirement. Okay, so if we move to another variable, let's say variable not found. Okay, variable not found is here, and this is def at node 2. It is used at node 2 and 8. Okay, so it also used at node 2 itself, and it used at the node 8 here. So if we do all depth coverage, let's say I want to pick the test requirement to be a little bit long. So I want to go from node 1 to node 8, right? So my test requirement will be 1, 2, 3, 4, 5, 6, 7, and 8. Then I find a test part that cover such test requirements. So I choose the test part coming from 1, 2, 3, 4, 5, 6, 7, 8, 10, going back to node 3, and then end at the node 11. And we satisfy this ADC for the variable not found. Okay, so here are the lists of all the test parts that are needed to satisfy the all depth coverage at node 1. Okay, so we have several variables that got initialized or defined at node 1. So subject, pattern, not found, ISAP, RTN index, subject learn, pattern length, subject length and pattern length, and the iPad variable. And we have these test parts to satisfy all of the depths that we need to ensure to go to every single used. Okay. So the next one is the all uses coverage. Similar thing, but now we cover more. So we need to cover all the uses of the same depth, right? So you have these for the subject, we have these for the pattern, we have these for the not found, so on and so on. Okay. And the last one is all DU parts coverage. So you list all the DU part first, and then you find all the test parts. Okay. All of these we focus only at node 1. Okay. So this one as well. All right. So there are many details in this kind of data flow coverage. So I think you need to have some time to go back to the graph, understand, try to list out all the test requirements for each of the coverage criteria, and see how we go to this kind of list of the test paths. All right. So to summarize, today we talk about another type of graph coverage criteria, which take into account the data flow of the data of the variables inside the graph. And this ends the criteria based on graph now. So we can see that the graph is a very powerful abstraction that we can use to define the test cases. And we can derive the graph from the source code. And by having this graph structure, we can use it to derive the test cases to make effective tests. And that's all for this module. See you again in the next module.